Now let's see the solution of test number 17. The question is, a high voltage copper transmission line has a diameter of D equal to 2 cm and length L equal to 200 km. A current I equal to 1 times 10 to the 10 cube ampere is transmitted to this line. How long does an electron take to travel through this line? Use electron density of copper N equal to 9.46 times 10 to the 28 per meter cube. In this problem, what we have to do is that we know that when there is a current passing through a wire, it means that there is the motion of the charge, and we know that in the conductor, like in the copper, the charge that moves is the electron. Okay, if the current flow in this direction or pass through the wire in this direction, the electron move in the opposite direction because the electron has a negative charge. Okay, and along the wire with the length L, the time that the electron takes is equal to L over Vd. Here, Vd is the average speed of the electron that move in the copper wire, or we also call this the drift velocity or the drift speed, okay, which is the average speed of the electron in the wire. And how can we calculate this average speed? Okay, we can write that the current that passing through the wire is equal to the NQVDA. Here N is the electron density, is the number of electrons per unit volume, and Q is the charge of each electron. Okay, so N times Q is the charge density, which is the charge per unit volume. Vd is the average velocity or average speed, and A is the cross-sectional area of the wire. Okay. How can we get this relation? This is quite simple. We can see that if we have electron that move in this direction passing through an area A, this is an area A, okay, and in the time delta t, we know that the electron that start from this area, start from this surface, this cross-sectional surface area, will move the distance Vd times delta t. Okay, the charge that follow this electron will move into this volume, and this volume, if we call this the delta V, this volume, okay, is equal to A times Vd delta t. It means that the first charge that is at the surface will move with this distance, and the charge that follow will go into this volume in the time delta t. Okay, and this volume is equal to A, which is the cross-sectional area, times V delta t, which is the length that the first electron move in time delta t. Now, the charge that move past this area is equal to the total charge that move into this volume, right? So that is the charge density NQ times the volume. So the total charge that pass this surface, this area, is the charge that move into this volume, and equal to NQ delta V. And from the definition, the current is a charge per unit time, okay, which is equal to the Q over delta T, and this is equal to NQ delta V over delta T. Okay, And when we express delta V equal to A VD delta T here, we can see that delta T cancel, and we have this term Q over delta T, which is I is equal to NQA VD, which is this expression. And by rearrange this relation, we have that VD is equal to I over NQA, and T is equal to L over D, and we substitute D equal to I over NQA here, so we have that T is equal to L over I over NQA, or L times NQA over I. Q is equal to charge of the electron, which is equal to E, right? And A is the cross-sectional area of the Y. The Y has a diameter of D. So the cross-sectional area is pi D square over 4. Okay, because I is equal to D over 2, so pi R square is equal to pi D square over 4. Okay, so we have the expression of the time that electron travel along the Y with the length L here, and we know all the numerical value of these variable. Okay, we have L is equal to 200 kilometer. Again, we have to change this into the base unit, so it is a 200 times 10 cube meter, right? We have D equal to 2 centimeter, and we change this into 2 times 10 to the minus 2 meter. Okay, and A is in ampere. Okay, N is in per meter cube, so it's okay. So we can use this numerical value and put to this expression. And when you do the arithmetic, you will see that we have T is equal to 8.55 times 10 to the 8 second. This is very long time. If we convert this to 1 year, using 1 minute has 60 seconds, 1 hour has 60 minutes, 1 day has 24 hours, and 1 year has 365 days. We can convert this into years as a 27.1 year. It means that the electron from the electrical generator plant move through the line with 200 kilometers, which is normal, right? If you send the electric power from the power plant to the city, the distance can be like 100 kilometers, 200 kilometers or more. Okay, it take electron 27 years to move from the energy plant to the city. That is very long. It is very long time. But we know in practice that the energy can move from the plant to the city with the speed that close to the speed of light. Okay, and how can the electron move very slow, but the energy can move very fast from the plant to the city or to the user? It means that the energy does not transfer through the motion of the electron. You will learn later that the energy transfer through the electromagnetic wave that move through the conducting wire, which means that the energy can move with the almost close to the speed of light. Okay, this comes from the induced of the electric field and magnetic field that penetrate or propagate, not penetrate, but propagate through the to the wire, and that move with the speed close to the speed of light. It's not the electron that carry the energy from the power plant to our house.